Alright, so today we'll be continuing our study of vectors, and specifically we'll be going over a different way of representing vectors. So before we go into that, let's talk about unit vectors on the axis. So if we have two vectors here, I over here and j over here. Now I is pointing in the positive x direction. So this is a horizontal vector pointing in the positive x direction, and note that the coordinates are 1, 0. So that means it's got a magnitude of 1, making it a unit vector. And j is very similar, except it's pointing in the positive y-axis, meaning that it's a vertical vector, not a horizontal vector. And again, it's got a magnitude of 1, and that's in the y direction. So it's a unit vector as well. So as I mentioned previously, unit vectors are really great at changing the direction of different vectors. And that's why we're going to be using them to develop a new way of representing vectors called the ij notation. And as you can probably tell, it involves these two vectors. So if we have a vector u and it's got components x and y, so it's x units long in the x direction and y units long in the y direction, then we can write that vector using scalar multiplication. And what I mean by that is our vector is going to be the sum of the horizontal component multiplied by x. So what that's doing is here x is a scalar, so it's scaling it up. So let's say we were 5 units along the x-axis. Then our x here would be 5, because our x here would be 5. And that would take our 1 unit long vector and multiply it by a length of 5, meaning that our new vector will be 5 units in this direction, because it's going to be going in the same direction. But then, if we want a vector that's not on the x-axis, then we can multiply the j vector by y, and that'll change it in the y-axis. And then when we add these two, we get this resultant vector. And so you can sort of think of this not as just some coordinate points, and that these are where they are. You're actually now thinking of it in terms of vector, which is what the Cartesian coordinate systems really happen, what it's really doing. So we're going, this vector here is xi. So this is our I vector in the horizontal direction scaled x units along. And then up here, this is going to be our yj, which is our j vector scaled y units up. And when we add these two using the triangle rule or the parallelogram rule, doesn't really matter which, we get this resultant vector u. So this is just a different way of representing them. And if you've done physics, you may have seen this notation before, depending on what your teacher uses. But this is very commonly used in the sciences, and it is also really useful in the mathematics, because it's thinking of it less so in terms of just an arbitrary coordinate system and more so in terms of vectors. And we use this, you'll use this a lot if you do any mathematics at university, because vectors comes up a lot. All right, now moving on, we can look at some examples. So if we want to write each vector in the form of xi plus yj, well, this is actually really simple. So this is just a point, and so it's actually going to be a vector that starts at the origin and goes to 3, 2. So if we want to represent that using our xi plus yj notation, well, this is just going to become 3i, because we're 3 units along the x-axis, plus 2j, because we're 2 units along in the y-axis, and j points in the y-axis. So this will be our vector. And so it's really simple, and there's nothing too much to it. And so if we do that over here, we're going to get minus 3i and plus 5j. So again, that's really not that hard. We're not when we're working with position vectors. But what about this vector? So this vector doesn't start at the origin. It actually starts at minus 2, 1. So what we're actually going to do is we're going to move this to the origin, and then we're going to think about it as a position vector. So what do we have to do to move this to the origin? Well, we have to move our point A down 1 and to the right 2. So what we're going to do over here with B is we're going to move this down 1 and to the right 2, because that way we'll have moved we'll have moved both ends. So that means our B should be over here, and our A should be here, So then if we draw a vector pointing towards it, note that it's got the same gradient going down. So that means it's pretty much the same vector. We've just shifted it across 2 squares and down. So now our B is actually at 4, because it's 4. And if we go across, that's going to be -2. So now our position vector is 4, -2. So that would mean in ij notation, it's going to be 4i minus 2j. And note that because this vector has this new AB vector, the black line, is now got the same magnitude and direction, it's still the same vector. It doesn't matter that we've moved it. And so that's basically it. So if you've got just a basic, like in the first 2 examples, this one and this one, if you've just got a basic position vector, then you can just convert it straight to ij notation. And if you don't, then you have to move it so that it is a position vector, and then you can convert it to ij notation, which still isn't that bad. So now we can also, you do addition and subtraction using these components, and it's just the exact same thing. So previously, when you would just add the x components and the y components, you now do the exact same thing, and same with subtraction, except you add this I and j, and you basically just write it in the new way. But other than that, essentially nothing's changed. So looking at some examples of that, given vectors v and w, so v is 4i plus 7j, and w is -i minus 3j, we want to find v minus w. So the question is v minus w. So what is our v? Well, our v is 4i plus 7j. So we've got, I'll just put a brackets around this, 4i plus 7j. And then we want to subtract this vector, which is -i minus 3j. So here we're going to add the I components and the j components separately. So what I'm going to start with, I'm going to put bracket and a bracket. I'm going to put my I vector, and I'm going to add bracket, bracket, j vector. So now let's look at the coefficients of my I and my j's. So in front of this I, I've got a 4. And then in this side, I've got, this is a minus sign, so that's going to be -1. But just note that there's a minus sign here. So that's going to have to come inside on this minus, and it's going to have to come inside here. You should already know that, but it's a very easy mistake to make, to miss that we have to change all the signs. So this is going to go from a -1 to a +1. And over here, I've got a 7 in front of my j. That's nice and easy. But then it's going to be -3, so that's going to become +3. So what I'm actually going to get is v minus w is going to be 11, sorry, not 11, I added that up. I added that wrong. It's going to be 4 plus 1, so that's 5i plus 7 plus 3, which is 10j. And so that's going to be our v minus w vector, 5i plus 10j. And note that you get the same thing if you were to just add straight across, sorry, rather subtract using the previous notation. And so moving on to the next example here, we want to write OA equals to 3 minus 1, and OB is equal to 2, 6 in component form. So what they mean by component form is we split it up into our A, I, and J components. So OA is equal to 3 minus 1. So then we're just going to use exactly what we did in the last example. So this is going to become 3i minus j, just like what we were doing in the previous slide. And then we've got OB, which is equal to 2, 6. So then we're going to turn that into 2i plus 6j. And you can't forget to add that these are vectors, because they are. And so these are our two vectors in component form. And now in part 2, we want to find OA plus OB. And so we'll be adding them using our component form. So if we move over here, we want OA plus OB. And so that is going to be our OA, which is 3i minus j, 3i minus j plus 2i plus 6j, because that's our OB. 2i plus 6j. And so from here, we just do exactly what we did in this example up here, and we just add our components. So I've got a 3 here in front of my I, so I'm going to go 3, and it's just a plus and then a 2, so I'm just going to be plus 2 on my I, bracket, those are my I components, plus, bracket, I've got minus 1 in front of this j, so I'm going to put a minus 1 here, plus 6, that's going to be plus 6, and then those are my j components. And so from here, I end up with 5i, not 5j. So from here, I end up with 5i plus minus 1 plus 6, which is 5j. So it's going to be 5i, 5j. And that's it. And so that's what happens when you add those two vectors. And this notation, it may seem a little bit useless now because we're just doing the exact same things with it. But later on, we'll be working with this notation more. And that'll let us it'll make it a little bit clearer and a bit easier to work with vectors in the future because now we're defining everything in terms of two component vectors. All right, so let's move on to this. So if we're given this vector, v, and it's minus 5i plus 4j, we want to find 8v. And that little vector sign is under all of this. It should actually be over here, just because that 8 is a scalar, because it's just a normal number, and the v is the vector. But it looks like it's just moved a little bit. Anyway, so this just represents that we can actually do scalar multiplication using this notation as well. We're not just limited to addition and subtraction. So if we look at 8v, then this becomes 8 outside of minus 5i plus 4j, and that's just when I substitute in from here. And so this becomes, and it's just going to be just like you would normally expect, you just multiply out the components. So it's just like any expansion of brackets, and you should get it in the same form. So it's going to be 8 times minus 5, which is minus 40i. And then it's going to be plus 8 times 4, which is 32. 32j. And so 8v is minus 40i plus 32j. And that's it. So what have we learned today? We've learned how to represent it using this represent vectors using ij notation. And we've also learned that you can do addition and subtraction as well as scalar multiplication using this ij notation. And it's not that different from the normal notation we use, except we're now defining it in terms of these vectors. Anyway, I hope that this lesson was helpful, and I'll see you guys next time.